So a few episodes ago, we were talking about products. And a product, here, I'll use the set notation. A product A cross B is an object with maps instead of pi for projection. I'm going to use the same notation I did last time. So first and second. And this is a projection onto A and a projection onto B, such that for every other object, well, for every object with maps to A and B, call them F and G just for the sake of argumentation, there exists a unique map from Z to A cross B, such that doing this map and then first is the same as F, and doing this map and then second is the same as G. So this is called a binary product. We showed that you could get products using prod n A, B, where A and B were contracts. And that unique map was function Z return f of z, comma, g of z. So this is going to be a pair, and since f maps from z to a, it'll pass the A contract, and when G maps from Z to B, passes the B contract. So this is an element of the set of pairs where the first one's an A and the second one's a B. And if we take the first one, that's clearly the same as F. And if we take the second one, that's clearly the same function as G. So this is our implementation of products. And then we saw that the nullary product, rather than the binary product, at least I suggested that the nullary product looks like this, that it has no contracts, but that still allows for exactly one value to pass this contract. Right? There were no contracts passed in as parameters to the list, but this still produced a contract that expected exactly one value, the empty list. Now in JavaScript, all functions take at least one value. You might say, hey, but what about this? Well, it's still invoked with an empty list of arguments. You still have the arguments object, and this behaves just like an empty list. Okay? So what you're actually doing is invoking it with the unique value empty list. So how can we characterize the empty list as with a universal property? What can we say about it? Well, we can say, if we call T, the T equals this contract, then it is true that for every object, Z, there exists a unique map from Z to T. So if I drew this using set notation, in this set there's a unique object that I denote with brackets, and in this set Z there's a whole bunch of objects, and the only thing you can possibly do where the output of this function passes that contract is map all of these inputs to the very same output. No matter what you provide for Z, this is the constant function that spits out the empty list. So there really is a unique one that can go to it. And I've used the letter T because in category theory this is called a terminal object. There's a morphism from every other object into this one. It's like the end of the line. Let's think about some other terminal objects in other categories. All right? Well, say we have natural numbers under divisibility. So, natural numbers and divisibility. And we saw that the product, the binary product, was called GCD. Well, what is the GCD of no items? Well, it'll be a number, T, such that given any other number, Z, natural number Z, Z divides this thing. There is no such number. Any natural number you pick only has a finite set of divisors. So if we augmented the natural numbers with an extra number infinity, then we might say infinity is the terminal object. But if we're just looking at the natural numbers, it has no terminal object. Okay. What about less than or equal to? And this, again, we'll say natural numbers rather than all integers. Does this category have a terminal object? Well, it would be a natural number T such that for all natural numbers Z, Z was less than or equal to T. Again, there's no such number. It would have to be infinity if it existed at all, as infinity is the only thing that every number is less than or equal to. So again, this category has no terminal object. Okay. How about something we'll call pointed sets? Pointed sets. A pointed set is a set equipped with a function from the one element set into the pointed set. So if we call the pointed set P, this picks out an element of P. Now notice that the empty set cannot be pointed because there's no function from the one element set to the empty set. You have to choose something to assign this to, and this doesn't have anything that it could possibly map to. So there isn't the empty set is not a pointed set. Okay? Now a pointed function, let me clear this up a bit. A pointed function is like a normal function, except that the special point that's picked out here has to map to the special point in the codomain. So if I've got a pointed function f from the pointed set P to, and I'll put a little point there, remind us that it's pointed, to the special set Q, then there will be a special point in P, picked out by this thing, and there will be a special point in Q, and this special point has to map to that special point. So, does this have a terminal object? Well, for every pointed set Z, there has to be a unique function from Z into T. Well, if T is again the one element set, and that's the only thing that could be the special point, well, every set Z is going to have to map to that point. So pointed functions between pointed sets does have a terminal object. That category does have a terminal object. Now, I said that if you turned around all the arrows in the product diagram, you would get a co-product diagram. When we turned around the arrows in minimum, we got maximum. When we turned around the arrows in GCD, we got least common multiple. When we turned around the arrows in, turned around the arrows in sets and functions, instead of pairs of sets, we got the disjoint union of sets. So let's see what happens when we turn around the arrow in the definition here. Well, what do we get? We're going to get a set that I'll call I for initial, because it's beginning, such that for all Z, instead of going into I, it comes out of I. And there's a unique way to do that. Let's start with sets and functions first. What set exists such that there's a unique function into here? Well, if we count the number of sets, count the number of functions between two sets, say we've got S and T, and we want to know how many functions there are from S to T. Well, if S and T are finite, then for each element of S, I can pick one of the elements of T. And say T has little t elements and S has little s elements. These two are numbers. Right? Well, that means for the first element, I get to pick T. And for the next element, I get to pick from T again. So that's T times T. And for the next element, I get to pick from T again. So that's T cubed. And so if there are S elements here, I get to pick from T different possible outputs for each of them. So that means there are T to the S functions from S to T. Now if we think about that, say we restrict to finite sets, what could I be such that Z to the I is always 1, no matter what we pick for Z? Well, anything to the 0 power is 1. So that suggests that the empty set is I. And indeed, if this has nothing in it, then there's only one trivial function that doesn't assign anything to the no elements that are in there. There's the one unique function from the empty set into any other set. So, in the category of sets and functions, the initial object is the empty set. Let's check our other ones. Say we've got natural numbers under divisibility. I'll go in that, and I'll just do this to remind us it's divisibility. Well, instead of GCD, the coproduct was LCM. What is the least common multiple of zero objects? Well, it's a number I such that for all numbers z, I is a factor of z. Well, that's clearly 1. 1 is a factor of every number, every natural number. So in the category of natural numbers and divisibility, the initial object is 1. It didn't have a terminal object, but it does have an initial object. Let's try it again for less than or equal to. So we've got natural numbers with arrows that mean less than or equal to. I is a number that is less than or equal to every other number. Every number. Well, natural numbers have a lower bound. 0 is the smallest natural number. So, 0 is the initial object in this category. Again, the category does not have a terminal object. It would have to be infinite. And the natural numbers don't include infinity. But it does have an initial object. How about pointed sets? We want, just a sec. We need pointed sets with pointed functions between them. We need some set, some pointed set called I, such that there's a unique function into every other pointed set, z. And when I say other, because I keep making this mistake, I'm actually including this. So every set z, for all. It's not for all except this one. It's really for all. Well, this is a pointed set, so it's got to have its special point, and z, no matter how many other elements it has, it too has a special point. And this one has to map to that one. Well, what if we didn't have any other objects here? Then this one maps to that one, and we don't have any other choices. There's exactly one. So in this category of pointed sets, the one element set is both initial and terminal. There's a unique map into it from every pointed set, and there's a unique map out of it from every pointed set. And this is really what JavaScript is like, in that there's no way to invoke a JavaScript function without passing at least the empty list of arguments. So it's pointed in that way. And so the empty list is both initial and terminal in the category of contracts and guarded functions. Now, I said that, but we could decide to change our mind about what we qualify as a contract. So if we wrote a contract, function x where nothing past it, maybe we could construct something that has the empty set of values past this. So if it, for example, if we just, the only thing we did inside this was throw type error. Well, nothing would pass this. Could we use this as our initial object? Well, we could do it this way. If we said function with nothing, and then we didn't pass anything to this, because what would we invoke it on? Then we could go on, but we'd still be able to return a value. And so, because we're still able to return values, even though there are no functions from the empty set to another guarded contract, we really can't shoehorn in the idea of an initial object into our category of contracts and guarded functions.